Right, I'm going to do a quick video to do with extension and energy transfers in springs. Right, the main things I'm going to cover is what is the spring constant of a spring? What is the equation that relates the force and extension of a spring? And how do we calculate the work done in stretching a spring? Right, so what is the spring constant of a spring? Well, the spring constant basically tells you how much force is needed to make the spring stretch by a certain amount. I always like to base my explanation on the calculation, so starting with the calculation is a good place to start. So if we start with force equals spring constant times by extension. And then if we rearrange the equation, we could just put F equals K times by X, or sometimes it's E instead of X. So let's rearrange that to get K, the spring constant. So spring constant is going to equal F over X. Right, the units of force are newtons and the units of extension is meters. So that means that the units of the spring constant is going to be newtons per meter. So in other words, the spring constant tells you how many newtons of force you need to put onto the spring to make it stretch by a certain amount, and we usually say per meter. So how many newtons it takes to stretch the spring by a meter. Now you might get some springs that are pretty thick. Now they're going to take a lot of force to make it a stretch. So we see it's got a large spring constant because it's stiff. So the K value could be like 500 newtons per meter. So you'd need to put 500 newtons on to make it stretch a meter. Whereas some other springs might just be skinny and they are not stiff. So that would have a low spring constant. So that would be easy to stretch. And the K value, the spring constant, might only be 50 newtons per meter. So this big spring over here is sort of 10 times stiffer than this one. So the spring constant tells you how much force you need to put onto a spring to make it stretch a meter. Now that's the same as how much it would take to make it compress by a meter. So if you had a spring that was already stretched out and you were squashing it, so compress means to squash it. So that could be like the springs in your car suspension, where at first they are quite stretched out, and then as you go over little bumps, the spring compresses. Now the second thing that I was going to cover, what is the equation that relates the force and extension of a spring? Well, I've already covered it here. Now you might get asked to calculate the spring constant from a force extension graph. So if we look at a stiff spring, what that basically means is you need a big force and it's only going to produce a small extension. So the line will be steep like that. And if you've got a spring that's not stiff, that means that you only need to put a smaller force on and you get a large extension. So let's relate how stiff the spring is to the steepness of the gradient. So stiff spring is a steep gradient or slope, and when it's not stiff, it's a flatter slope. And a large force produces a small extension. And with this one, a small force creates a large extension. That's how you would get about 3 marks for explaining what the gradients show. Now let's have a little look and see what the gradient tells us. Now that's called your y-axis up the side, and that's called your x-axis along the bottom. And to get the gradient, you always do y divided by x. And in this case, y is the force and x is the extension. Now if we rearrange this equation up here, f equals kx, well, if we do f over x, that's going to equal k. So basically this gradient is going to give us our k value, because we've got force divided by extension is the gradient, and force divided by extension is the spring constant. So the spring constant is the gradient. So all you need to do is work out the gradient, and it means you've worked out the k value. So sometimes they ask you to work out the k value by popping some numbers in, or sometimes they ask you to work out the k value by looking on the graph. But they won't tell you that you've got to work out the gradient. That's why I'm telling you now. So if we did 30 divided by 0.1, that'll give us our gradient, which would be 300 newtons per metre. Remember, the units of the spring constant is newtons per metre. Extension was in metres and force was in newtons. And if I was to work out this one, the k value would be 10 divided by 0.3, which is 33 1/3. So you can see this spring over here is much stiffer. It takes 300 newtons to make it stretch by a metre. Whereas this spring over here only needs 33 1/3 newtons to make it stretch a metre. Now make sure that you realise you can only use a force extension graph to calculate k while the graph is linear. If you put too much force onto a spring, it's going to start to stretch like that in a non-linear way. And that's because you've exceeded the elastic limit, which I've explained about in one of my previous videos. The elastic limit has been exceeded. We've gone beyond the elastic limit, and the spring is no longer behaving in a linear way. It's behaving in a non-linear way. So this area here is elastic, and this area here is plastic deformation. So this equation no longer applies for the non-linear section. Now students often say, "Sir, which part of the graph shall I work the gradient out for? Where do I use my values?" Right, it doesn't matter. Because it's a straight line, you can take any value and divide it by its corresponding value, and you'll come up with the same number. Now the final thing I want to show you is how do I calculate the work done when we're stretching a spring. Right, so just say you've fixed a spring. As soon as I start putting a weight onto the spring, that spring is going to stretch. Now how much extra it's stretched That's the extension. And to get it to extend took energy. Now you can work out how much energy it takes to stretch the spring by using this equation. 1/2 times by the spring constant times by the extension squared. Energy's in joules, the spring constant's in newtons per metre, and the extension is in metres. And we're squaring it, so that'll come out as metres squared. And if we simplify it, we just say E equals 1/2 kx squared. Now you can either just work out the energy if the examiner gives you the values to pop in, or they might ask you to work it out by using a graph. Right, so the way we use this equation is they might ask you to work out the energy. So you just pop the numbers in. Let's just say K was 300 newtons per metre. If we have a little look at our other graph there, we'll say when the force was 30, the extension was 0.1. So we don't actually need the force, we just need the extension, which I've just said was 0.1. Remember to square that. So that gets squared first. So 0.1 squared is basically 0.01. And that comes out as 1.5 joules. So that's how you would do that. So I hope the video was useful. Work hard, be nice, and I'll see you in the next one. Bye for now. Well, I hope the video helped you. Work hard, be nice, and bye for now.